All right, let's jump into our first speaker. Our first student speaker is Ian Nelson, and Ian is at Cal State University Long Beach. He's pursuing a Master's of Science in Geographic Information Science. His advisor is Dr. Suzanne Welcher. And the research I believe he's going to be presenting today is work with Dr. Desi Underwood, who many of you know, who's the director of the Streams Ecological Assessment Laboratory at Cal State Long Beach. They're investigating how stressors correlate with IBI scores in the Santa Ana Watershed. So let's bring Ian up. Welcome, Ian.
Hi everyone. Thank you, Matt, for that introduction. Today I'm going to present the results and maps I produced for my master's thesis titled The Bioassessment of Stream Health in the Santa Ana Watershed Using Geographic Wave Regression. And I'm also going to provide some information today about how GIS is useful for bioassessment. Real quick, the study area, Region 8, located in Southern California. The Santa Ana Watershed flows from the San Bernardino Mountains through urban, industrial, commercial, and agricultural land use types before entering the Pacific Ocean. The Santa Ana Watershed covers 4 counties: San Bernardino, Riverside, Los Angeles, and Orange County, and as of 2010, approximately 6 million people reside in the Santa Ana Watershed. This is a map of the study area, and the purple lines indicate the county boundaries. Oops. And sorry about that. Is everybody done? Oh, here we go. Okay, this is Los Angeles, this is San Bernardino County, Riverside, Orange County, further south is San Diego County, and this is the Pacific Ocean. For this presentation, I'm only going to be focusing on the results from the Santa Ana Watershed, and the blue dots represent the 750 random stream sites generated through the probabilistic design. And Dr. Desi Underwood, Director of Streams Ecological Assessment Laboratory, and Biological Department Chair for California State University Long Beach, stratified the stream sites into 3 elevation strata indicated here. And this was based off of the geography of the Santa Ana Watershed. And then she performed regression analyses with the respective elevation strata. So these are the stream sites that were sampled. In the total column over here, this is the 750 random stream sites generated through the probabilistic design. These are the stream sites sampled from 2006 to 2011. This is the total number of stream sites sampled. So there's 182 stream sites sampled in the Santa Ana Watershed. And this is the elevation, or I mean, the strata, the elevation strata. And SA stands for the Santa Ana Watershed, SJ stands for the San Jacinto Watershed. And for this presentation, I'm only going to be focusing on the Santa Ana Watershed. And due to user requirements for the regression methods provided by ArcGIS, this middle strata was split in half and grouped with the respective elevation strata. This will make more sense in the following slide. So GIS is useful for visually representing the data, for understanding the geographic patterns of BMIs, for spatial statistics, for trend monitoring and identifying areas of interest, such as regions of streams that are most at risk, and for facilitating this information to stakeholders. So real quick, I just want to get into the data. Watersheds and rivers were provided by calwater.org. A base map was used from Esri's ArcGIS, and the index of biological integrity and stressors monitored for stream health were provided by Dr. Desi Underwood. And this is a flowchart of the methodology that I used. So the IBI data was organized into 2 Excel sheets, one for stream sites under 525 meters and one for stream sites over 525 meters. So this is the revised elevation strata. From there, I displayed the XY coordinates of the stream sites and then projected the data to NAD 83, which stands for North American Datum 1983. And when you're measuring distances, or when regression methods are incorporating distances into their equations, it's important to project your data. From there, the projected stream sites were then buffered with a 150-meter buffer to represent the reach of the stream. And then the buffered stream sites for the respective revised elevation strata were then investigated using this exploratory regression tool. It's the multivariate ordinary least squares regression. And during this process, I investigated lots of variables in accordance with SWAMP. So these are variables such as alkalinity, turbidity, or conductivity, pH, nitrates, nitrites, etc. And from there, it generates a statistical results table, and the consistent significant variables were then further investigated using this geographic weighted regression. This geographic weighted regression is a weighted least squares regression that provides useful statistics that can be mapped. And so this regression method provides a global statistics for the whole study area, and this regression method provides statistics for every stream site. And it also produces a feature class, which combines the buffer, which has all the buffered stream sites, and the corresponding statistical results. So this is the first map I created. This is a hotspot analysis of IBI score from 2006 to 2011. And real quick, just to give you some geographic perspective, this is Los Angeles. These stream sites are in San Bernardino. These stream sites are in Riverside, and then these stream sites are in Orange County. And what we're seeing are the geographic patterns of, and this slide kind of relates to what Catherine was talking about in the Malibu Creek watershed. And what we're seeing is this is the interpretation of the IBI score. So these red stream sites are indicating a score of 0 to 19, which is very poor. And these yellow stream sites are indicating a score 40 to 59, which is the cutoff of impairment. And the green are indicating very good. So we actually only had one stream site that scored very good. So what we're seeing here is in the upper portion of this watershed, which is mainly comprised of forested land use types, we're seeing that the range in IBI score is ranging from fairly good with a few sites and very poor. And as the watershed flows west towards the Pacific Ocean, we're starting to see along the Santa Ana Washington Watch that the IBI score is becoming very poor, or poor to very poor. And we think what's going on with this regions of the watershed is that there's a lot of recreation use, a lot of day use activities going on within these regions, and that might be negatively impacting the IBI score. From there, the watershed flows through different land use types, and these stream sites are mainly comprised of agricultural land use, and we're seeing high levels of nitrates and phosphates, and also contributing to very poor IBI score. And as the watershed flows west towards the Pacific Ocean, it goes through a mix of land use types from urban, commercial, and industrial, combined with highly altered stream sites, and we're seeing a consistent very poor IBI score. So this is a comparison of Underwood's 2011 technical report with the revised elevation strata regression results. And so these stressors were investigated further. And what we're seeing is in red is indicating a negative relationship, green is indicating a positive relationship, and the asterisk represents the level of significance. So one asterisk is representing a p-value less than 0.10, two asterisks represents a p-value less than 0.05, and then three asterisks represents a p-value less than 0.01. And the results are quite similar. So what we're seeing is for the lower elevation stratas, we have a significant negative relationship, similar here with the revised elevation strata. And for the stream sites that are in this upper portion, over 700 meters, we're having a significant negative relationship, and again, a significant negative relationship. And so the results are similar. So this is evidence that provides that the results from the revised elevation strata are validated with Dr. Underwood's 2011 technical report. And one thing I just want to point out is with this dissolved orthophosphates is that it's showing a positive relationship for the whole study area. And I'll get into more detail with this in the following slides. So this map is can be a little confusing, so I'm going to take some time to go through it. This is the spatial patterns of pH coefficient correlated with IBI score. So this map is no longer representing the IBI score, or the range in IBI score. This outer circle is represented by this donut legend, and the dark red hues are indicating the strongest negative relationship with IBI score, and these light pink hue is representing the weakest relationship. So if we were to look at these coefficient values, and if you were to take the absolute value or remove this sign, the higher the value indicates the strongest relationship with IBI score, and as this value approaches 0, it has no relationship with IBI score. And the little circle inside the donut represents the actual range in pH values. So we have a range in pH values from slightly acidic, from 6.33, all the way up to highly basic for stream size. We're seeing some stream size with pH all the way up as high as 10.49. So what I'm trying to do is I'm incorporating 2 types of quantitative data to investigate the spatial patterns of these stressors. So what we're seeing, the overall spatial patterns, what we're seeing is that stream sites that are associated with a range in pH of 10 or 9, and then some stream sites that are associated with pH that exceed 8.0 are the strongest negatively correlated with IBI score. And we're seeing that as the pH becomes more acidic, like up in this region of the Santa Ana Watershed, we're seeing that it has the weakest relationship with IBI score. And again, some sites down here that are more acidic are having the weakest relationship with IBI score. So the overall pattern, as pH exceeds 8.0, these stream sites are starting to have a negative relationship with IBI score. This is a map of the spatial patterns of pH. Sorry about that. For the upper portion of the Santa Ana Watershed, this is for elevation strata over 525 meters. And this is a similar pattern. The donut, the outer circle represented in this donut legend represents the strength of relationships. So the darker the hue represents the strongest relationship. And what we're noticing is this along Mill Creek Canyon is that pH ranging, or basic pH ranging over 8 has the strongest negative relationship with IBI score. And as pH becomes slightly acidic, we're seeing that it has a weaker or no relationship with IBI score. And what's really interesting here is that there's some stream sites that are really acidic, and we're actually finding out that these stream sites are also negatively correlated with IBI score. So there's kind of like an optimal range of pH that's around this 6 point, and it's kind of consistent with the EPA findings, which they state that BMIs prefer a range in pH from 6.5 to 8. And so this is the spatial patterns of dissolved orthophosphates. And what we're seeing, this is the first example of where we get into a little bit of heterogeneity within the watershed. So for the global ordinary least squares regression, it was showing a positive relationship. And using this geographic weighted regression allows us to look at the local variation within the watershed, and we're actually uncovering that some stream sites are displaying a negative relationship. So we're seeing that stream sites associated with values of dissolved orthophosphates over 1 milligram per liter. Some cases there's stream sites all the way up to 4 milligrams per liter. We're seeing that those stream sites are the strongest negatively correlated with IBI score. And as the range in orthophosphates gets really low, we're seeing that it has a positive relationship with IBI score. And again, we're seeing some negative relationships near the San Diego Creek here with higher levels of dissolved orthophosphates. This is the last map I created. This is a map of the spatial patterns of nitrates for the upper elevation strata. And again, this is a consistent theme, but what we're seeing here is that this is what we're not expecting these results. And what we're going to cover is that low levels of nitrates are negatively correlated with IBI score. And we thought that high levels of nitrates would be negatively correlated with IBI score. But what we're seeing is that, so these levels that are nitrates that are less than 1/2 milligram per liter are strongest correlated with, or negative correlated with IBI score. And that as the value or the level of nitrates increases, is showing a weaker relationship. But this is not incorporating how nitrates are interrelated with other stressors. This is just specifically looking at how nitrates is related with IBI scoring. And so, the results and visual representation are found around consistent, significant relationships, supported with literature review, and validated with Dr. Underwood's 2011 technical report. And the relationships within the Santa Ana Watershed, and the relationships among stressors and stream health in the Santa Ana Watershed are interrelated and vary geographically. And we can more precisely locate stressors that are negatively affecting BMIs using the geographically weighted regression. And our understanding of water quality is improving through different aggregations. And then, so for suggestions for future use, census tracts and block groups can be incorporated into, and we can start looking at different demographics, including total population, economics, etc. And you can also look at the area. When you start to look at demographics, you want to create a weighted area for that stream site. So if you create a buffer around that stream site, you would take the area of that buffer and divide it by the area of the census tract that buffer resides in. And that way you can get a better idea of what kind of demographics are maybe impacting the IBI score. And land use can also be incorporated. We've been seeing a few presentations about how land use might be impacting IBI score. And then investigating these relationships between stressors, there's a couple of cartographic techniques, bivariate mapping and multivariate mapping. These are ways to investigate multiple stressors. So you can, bivariate mapping is a way to look at 2 stressors, and multivariate mapping is a way to look at more than 3 stressors. That's all I have today. Thank you very much. Any questions?